The next talk is by Fengcheng Wu, who is at Wuhan, who's going to talk about fractional churn insulators.
Okay, thanks. Thanks for the organizers for bringing me back. I'm Allan's previous student. I was here from 2011 to 2016, and then I moved to Allan and University of Maryland as a postdoc. At Maryland, I was with Shanghai Sama, and then I moved back home at Wuhan University. Today's talk, I will focus mainly on Moiré physics in TMD, particularly on topological physics in twisted MOT2. So this work started with Allan, and then I will discuss a theoretical approach to understand fractional chain insulators. So the approach is also inspired by Allan's work. So there can be a mapping between chain bands and number levels, and this gives rise to a very natural way to understand fractional states in states without field, without magnetic field. When I was a PhD student with Allan, we studied the optical properties of semiconductor transition metal dicalcinides. So here's a slide that compares the graphene system and the TMD system. So graphene is a semi-metal and TMD is a semiconductor. So this is a crucial difference, and this leads to reduced number of degrees of freedom in TMD systems, and this leads to theoretical simplification. So roughly speaking, there are two values times one spin times one band in TMD, and this makes theoretical modeling much easier compared to the graphene system, and the energy scale associated with TMD systems are also relatively larger than graphene. Partly because it has a mass in TMD, and the graphene is massless. The first study that we performed in this Moiré TMD systems is on optics, and not directly on electrons. So this is the work with Allan back to 2016, and we finished the work in 2017 and then 2018. So the idea is that extons are composite particles. So they are composite electron hole pairs, and they can be understood as a particle, similar to electrons. So as a particle, it feels potential generated by this Moiré superlattice. And so the extons move in the periodic potential in the Moiré superlattice, and this leads to band folding. And the extons outside of the light cone are folded back to the light cone, and then there can be extra exton absorption peaks, and this is a contour picture. So without Moiré in monolayer, for example, MOS2, there is a strong exton peak, and with the Moiré potential, this exton peak splits into multiple peaks, and this, in some sense, is a standard textbook solid-state textbook problem, but physics is quite rich, and this prediction was indeed observed. So there are, in 2019, there are 4 back-to-back Nature papers, one from Yulin's group at Austin, and the other from Berkeley and from Xiaolong group, and then the 4th paper from the Europe group. So essentially, all reported the splitting of the exton peak in this Moiré superlattice. So I showed 2 of them here, and at this time in 2019, I think it's mostly called evidence or signature, as you can find in these titles. But now I think this is well established, and Moiré exton is there, and this there is a huge development following these works. So there are Moiré polariton, Moiré Rydberg extons. So the physics, the phenomenon is quite rich. This is following this exton work, we realized that electrons in this system can also feel potential generated by this Moiré superlattice. So I think in graphene, this potential is not very significant, and people do not talk about it. But here, this potential is significant. So we have a very simple Hamiltonian. Suppose we have this detour bilayer, meaning that the band alignment leads to this essentially one band near the Fermi level. And then we can make a very simple, wake up a very simple Hamiltonian, which is a particle, parabolic particle moving in a periodic potential. And this periodic potential has the periodicity of the Mori superlattice. And this is a textbook problem, and we can solve it using the Bloch theorem, and we get this mini band. And if we focus on this first Mori mini band, then we can map it to a tight binding model on the triangular lattice. The triangular lattice are formed by the potential maximum, in this case, of the potential. And we can map it to this tight binding model, and the hopping parameter can be tuned by the twist angle, or essentially the Mori period. As you can expect, as the Mori period increases, the hopping parameter decreases exponentially. So this is the single particle part, and for the interaction strength, the interaction strength turns out to decay in a power law way as a function of the Mori period, because interaction is 1/r if we take the Coulomb interaction. So the interaction strength decays slower than the hopping parameter, and this can lead to the Hubbard regime, meaning that you can be much larger than t for a large range of twist angles. So for this system, there's no need for magic angle. The angle can be quite flexible. Again, this is a work with Anna and with Emmanuel Tutic also here. At the beginning, we imagine to realize Hubbard model, meaning that the on-site interaction is dominant. This can be achieved by metallic screening. But in reality, at least in most experiments, the off-site interaction, the non-range party interaction cannot be ignored. So this is we call it generalized Hubbard model. It's still on triangular lattice. With this model, we investigated it. We investigate the phase diagram using Hubbard with Professor Dasama here. And there can be quite a range of phase diagram depending on the filling factor. So here, the different states at different filling factors can be roughly understood as generalized Wigner crystals. For example, at filling factor equal to 1, it's a Mott insulator. If the spin exchange interaction is antiferromagnetic, then we can get this 120-degree antiferromagnetic state. But the magnetic state can be quite rich. So in the mean field level, it can be this 120-degree antiferromagnetic state. At fractional fillings, we can get this generalized Wigner crystals. For example, at 2/3, we can have this honeycomb lattice, meaning that 2 out of 3 sides are occupied and the other side is empty. Again, this idea works out. This is the initial paper. I think Allan is one of the authors of the second paper. So the 2 papers are from Cornell and from Berkeley. So here they used transport measurement, and they indeed find these resistive peaks at integer fillings and fractional fillings, and they identified it to Mott state and generalized Wigner crystal states. There is a very beautiful paper here from Cornell group, from Professor Kim Fai and Professor J's group. So they used optical measurement, a very smart technique. So they do not directly probe the sample layer. They use this sensor layer. They use this external sensing technique. With this technique, they can map out a lot of fractional filling states. These are correlated states, but without topology. So as you can see, there are many fractional filling states. So this is the Hubbard physics in this system. How can we get topology here? So to get topology, we need 2 identical layers. At least this is the initial proposal that we came up in this 2019 paper with Anna. So this model is for twisted TMD homobile layer. So we have two valleys, and the two valleys are essentially decoupled in the single particle limit, and we focus on one valley, and we have two layers. This is the same as graphene, but different from graphene, we have one band from each layer. But here in graphene, we have more bands. So the Hamiltonian is simpler than twisted bilayer graphene, but is in some sense derived from twisted bilayer graphene, from the Tracer MacDonald model. So here we have this 2x2 Hamiltonian. The diagonal part is the Hamiltonian. Within each layer, it describes the particle moving in the periodic potential. And there is a momentum shift, kappa plus, kappa minus. So this is the momentum shift is from the rotation between the two layers. And the off-diagonal term is the interlayer tunneling. And this term has the same form as the Tracer MacDonald Hamiltonian. The interlayer tunneling term, it's one of the 4 terms. And this Hamiltonian has several parameters: the Maury period, the effective mass, the potential strength, and the potential shape described by psi, and the interlayer tunneling. And these parameters, I should say, they are very hard to estimate. So there are still ongoing works that that aims to determine them more accurately, and but the form of the Hamiltonian is constrained by symmetry. So here the symmetry is this 3-point group. Okay, with this Hamiltonian, it's a 2x2 Hamiltonian. So we like 2x2 Hamiltonian, right? Because with 2x2 Hamiltonian, we can decompose it in terms of Pauli matrices, and the coefficient in front of the Pauli matrices are effective pseudo-spin magnetic field. So this is the way we define the pseudo-spin magnetic field. And there is a very crucial ingredient here. The magnetic field forms a texture. It forms a Skyrmian texture in real space. And it has a periodicity, the Maury periodicity. So it's really a Skyrmian lattice. And we can characterize the Skyrmian by its winding number. So it's either +1 or -1, depending on the sign of psi. I will go back to this point later. Because of this real space texture, we can expect topological bands in momentum space, but it turns out this is not always true, as shown in this phase diagram obtained also with Shankar. So this is a phase diagram in terms of parameters, and in part of the parameter space, the bands are indeed topological. The Chen number of the first band is either +1 or -1, but in this wider region, the Chen number can be 0. So the topology is parameter dependent, and in the topological part, we can find that the potential maxima forms a honeycomb lattice. The effective lattice is a honeycomb lattice, but in the topologically trivial regime, the effective lattice is triangular. So the shape of the potential, the geometry of the potential plays a crucial role here. In our initial estimation, we find that the parameter falls into the topological regime. And this is a band at a small twist angle 1 degree, around 1 degree. And the first 2 bands, as shown here, they have Chen number +1 or -1. But the total Chen number for the first 2 bands is 0. So we can map these 2 bands into an effective lattice model as shown here. And this effective lattice model is essentially the Allan model within one valley. And the phase within one sublattice comes from the momentum shift in the continuum Hamiltonian. Because we have 2 valleys that are related by time reversal symmetry, so we have 2 copies of Allan model. So here we get this effective K-Mali model. So this is a single particle physics here. And if we apply an autoplane electric field, then we drive imbalance between the 2 layers, and the layer polarization can drive the topological state to topologically trivial state here. This is our initial imagination. I'm not sure whether it could work out, And we mentioned this material twisted MOT2. And the reason we use this material is because its valence maximum is at K value instead of gamma value. And the gamma value physics can be quite different. You can find another paper by Allan. And in here we mentioned we stated that because bands narrow at a small twist angle, a rich set of broken symmetry insulating states can occur at an integer number of electrons per Maury cell. So by this sentence, we essentially mean the quantum anomalous Hall state at integer fillings, but the system is beyond our imagination, and this is a breakthrough. This is a breakthrough from last year. This is the first paper by Xiaodong Xu's group at University of Washington. So the reported optical signatures of fractional quantum anomalous Hall effect in twisted MOT2. So he will give the next talk, so I will not go into the details. And there is a back-to-back paper by the Cornell group. They reported thermodynamic evidence of this state. The final evidence comes from this transport observation. So these plots are from the Nature paper by Xiaodong Xu's group. The reported observation of both integer and fractional quantum anomalous Hall states in this system down to zero magnetic field by transport. And the quantization is quite remarkable from this plot. Before going to the fractional states, I want to advertise this phase diagram from my group at Wuhan University. So we map out the interaction-driven phase diagram at integer fillings at filling factor 1 and filling factor 2. The main message is that besides the topological states, for example, the Chen insulating states at filling factor 1 and the quantum spin Hall insulating states at filling factor 2, there can be many other competing magnetic states. For example, at filling factor equal to 1, there can be this 120-degree antiferromagnetic state. And at filling factor 2, there can be a competing antiferromagnetic state that destroys the topology. This is a phase diagram obtained from mean field. Finally, let me go to this fractional states. How can we understand these fractionalized states without magnetic field? I think I got the inspiration. So I mean, there are different ways to understand it. You can use exact diagonalization, and if you use a right parameter and then the ED spectrum indeed theorize to these fractionalized states. But how can we understand it analytically? Can we make a connection to fractional quantum Hall? And the answer is true, and the answer is provided by Allan in this. I will show the two papers. So let me go back to this Skyrmian lattice. So we can rotate the layer pseudospin to the local frame of the Skyrmian field. By this, I essentially mean by this unitary transformation, and this U is a unitary transformation, and this chi is a spinner that aligns or anti-aligns with the Skyrmian field, depending on this plus sign or minus sign. By applying this unitary transformation to the Hamiltonian, then we can get effective non-abelian gauge field denoted by this A field. So this A field is you can think it as a real space Barry connection. So this is the Barry connection, real space Barry connection in terms of the spinner in the real space. And if we look at this 1-1 term, this A11, the diagonal term, and you can think it as an abelian gauge field, and this abelian gauge field is quantized in the sense that within one Maury cell, the magnetic field produced by this A field is quantized to one quantum flux H/E, either -1 or +1, depending on the depending on the model parameter. So this Hamiltonian makes a connection between the Maury band and the non-dot level, because in this Hamiltonian we see magnetic field. And I should say that this magnetic field is quite high. It can reach up to, let's say, 100 Tesla. The reason is that the Maury unit cell is small in term if you compare to typical magnetic lens. And this idea was put forward by Allan in these two papers. I was very inspired by these two papers, and I want to ask a question. What is non-dot level weight of the Maury chain band? How can we quantify the resemblance between chain band and the non-dot levels? And we first take this Hamiltonian. This is an exact mapping. So this Hamiltonian is exact. There's no approximation. So we can, with this Hamiltonian, we can decompose the block chain wave function, the block chain band, in terms of dressed non-dot level wave functions. By dressed non-dot level wave functions, I mean that the non-dot level wave functions here, this psi minus or plus psi minus plus psi plus, are dressed by the spinors that are R9 or NTR9 with aligned with pseudo magnetic field. And we came up with a trick to find an analytical solution to this chi plus chi minus. So they essentially they carry chain number in real space, so they cannot be continuous and periodic, but it can be continuous and periodic, quasi-periodic. With this trick, we can determine the weight of the first Maury chain band on the lowest non-dot level, as shown by this red curve. It quantifies the resemblance between the two, the Maury chain band and the non-dot level. And for certain model parameters, we can find that the overlap can be high, up to about, let's see, 80%. So it looks very like non-dot level, 80% like non-dot level. Can we do better? Can we make this weight larger? The answer is yes. We can generalize this wave function to a variational wave function. We can replace this spinor by a more generalized wave function I call BR. Here, BR does not need to R9 or does not need to be aligned with a pseudo spin magnetic field. It does not have to be normalized, so it's more general in this sense. And it can capture the spatial variation of the density in this Maury chain band. By variationally optimize this function, we can maximize the weight of the chain band on this generalized non-dot level. I call this wave functions generalized non-dot level. And as you can see, that the weight can reach up to about 0.955, depending on model parameters. So, so this shows the wave function, the function BR in real space. This spatial modulation comes from the density modulation in the Maury chain band. So we know that non-dot levels are uniform. The density is uniform in real space, but for this chain bands, the density are not uniform in real space. And this slide shows the quantum geometry of the original wave function and the variational wave function. So the qualitative feature of the quantum geometry is captured by the variational wave function. So this slide is slightly mathematical. Let me skip it. So with this generalized variational wave function, we can construct generalized Laflin states. So suppose we have a Laflin state or any fractional quantum Hall states in the lowest non-dot level, then we can multiply it by BR. BR is in some sense the envelope function. And this equation gives us a way to generalize physics in non-dot levels to Maury chain bands. We did exact diagonalization to check whether this variational wave function can indeed give us the fractional chain insulators, and the answer is yes. And this exact diagonalization results, and different colors are from different wave functions, and the results overlap quite well. And there is a very interesting observation we have high overlap here around 0.9 degree twist angle, but at this twist angle, the FCI is not the strongest in terms of the gap. And the reason is that at small twist angle, the spatial variation of the wave function is also strong. And this variation of the wave function leads to reduce the gap. This is my last slide. And we parameterize the variation of BR in terms of this lambda f. If lambda f is 0, then BR is spatially uniform and physics is reduced to Landau levels, and we get Flatlands state at finite factor 2/3. If we increase lambda to its actual value in twist MOT2, we see that the gap between this ground state and the excited state remain finite, but it's reduced. And this shows the adiabatic connection between Flatlands state and fractional Chen insulating state in this system. And this reduction of the gap is due to this spatial variation, and this spatial variation has a tendency to drive CDW state, the charge density wave state. Okay, with that, I want to make a summary. So in this Morris superlattice, the Chen bands can be decomposed using generalized Landau levels, and somehow this Morris superlattice is provide a magic way to realize Chen bands that mimic Landau levels, and the emergence of fractional Chen insulators in this system without B field has a larger energy scale compared to fractional quantum Hall in Landau levels. And the reason is that the effective magnetic field is larger and the effective magnetic length is reduced. So this picture shows a summary of the connection between different topics in Flatland that Allan dominates. So both fractional Chen bands and Landau levels. With that, I want to thank Allan for the guidance and thank you all for your attention. Thanks.